In this chapter, we will be studying the derivative rules. In this lesson, we will be looking at implicit differentiation.
All right. Hi, everyone. So today we're going to take a look at implicit differentiation. Now, if you glance right down here, you'll see that that's not implicit differentiation, but there's a bit of method to my madness here. This isn't nearly so difficult as what we're about to do, but what I've noticed over years of teaching this is that when we get to implicit differentiation, there's often a misconception that pops up, and it's very clear by the work that students do that they don't really understand the nature of algebra. They can do algebra, but they don't really understand what they're doing. Now, to get implicit differentiation, it's not a matter of just being able to necessarily do it, like manipulate the symbols. You got to have a bit of an understanding as to what it is that we're actually doing. So what I want to do is I'm going to step us way back, and just talk about a couple of examples, and I will quickly speed us up to calculus. Please don't worry about that. But let me show you what I mean by that. When I show you this, 4 plus 4 plus 4 plus 4, okay, most of you, okay, are not looking at this and going, okay, well, that's simple. 4 plus 4 is 8. Okay, then I've got 8 plus an additional 4, that's 12, and then 12 plus that last 4 is 16. You're not doing it that way. What you're doing is you're looking at that and you're saying, okay, I see 4 of them. I see 4 4s, and you're quickly rewriting this in your head as a product. And then 4 times 4 is 16. Okay? Good. That's great. That's exactly what you want to do here. Now, here's what happens though. When we make the transition from arithmetic to algebra, okay, what we do here is we're asking students to think about what they're doing. It's not just the focus on the answer, some sort of numeric answer. It's about the process. So if I replace 4 here with x plus x plus x plus x. Now, I have, in fact, in the past, had students look at this and say, well, I'm not entirely sure what to do. I don't know what x plus x is. So that's a dead end. But the question is, what did you do here? When you saw those 4s there, what did you do? Well, there were 4 of them, so I rewrote that expression, and then I could do the multiplication. So what we're asking you to do here is to think about the process. The process. What did you do? Well, the process here, I have got 4 x's. So I'm going to write this now, this sum, I'm going to write this as a product. Now, granted, I can't now say what this is equal to because I don't know what x is. I don't know what it represents. But I do know that this is going to be equivalent to that. And that's really what algebra is about. Okay? Algebra is about the properties of numbers that stay the same regardless of what the number is. Regardless of what number it is that we're putting down here 4 times, okay, it will be 4 times that number to get the final result. That's how I shortcut that. Okay, so now that's important there that you catch that. Now, okay, it's not important that you know that x plus x plus x plus x is 4x. What's important is that you see the process, kind of that abstraction from here to here, and how we get to this 4x. Now, let's take a look at a slightly different example, but again, it's the same point that I'm trying to get across here. What is the sine of an angle in standard position whose terminal arm passes through the point 3, 4? Okay, so I draw this out. Here's my angle in standard position. There's my theta. And so I pick my point right here, and it's going through the point 3, 4. Now, how do I figure out the sine of that angle? Well, what I do is I drop the altitude. And when I do that, because it's going through the point 3, 4, I know that this horizontal distance is going to be 3. And this vertical distance is going to be 4. Now, I know that the sine of an angle, okay, is the y-coordinate of that point over the radius, okay, of the corresponding circle, okay, or I might say it's the opposite over the hypotenuse here. Either way, I got to figure out what that hypotenuse is. Now, how do I do that? Well, what I got to do here is I got to employ the Pythagorean theorem. So I'm going to make this 3 squared plus 4 squared is equal to r squared. So that's going to be 9 plus 16 is r squared. I know that that's going to be 25 is r squared, and then I take the square root of both sides. Now normally when I do that, I would give myself plus or minus the square root of 25, but I know that it's got to be positive because the radius isn't defined such that it can have a negative value. So the radius is 5 there. And now I can go back and say, okay, that's 4. I know that the radius is 5, so the sine of that angle is 4/5. Wonderful. Now, same process, but let's change the question slightly. Let's say that the point is 3y. Let's just say 3y. And just to be fair, in quadrant 1. Okay, so same question as before, but just we're going to have it go through 3y in quadrant 1. So I draw this out. There's my angle, theta in standard position. It's going through the points here, 3 comma y. Now, I have had students, because we've actually used a question, we use questions similar to this on assessments and whatnot. So we talk about it in class, because it's a good question. It's a good question about getting students to focus on what you do. Now, I will have students that look at this and say, yeah, but I'm looking for the sign of this unknown, and I've got another unknown, and they stop. Because they look at this and say, well, I don't have a value. But I'm not asking for the value at that point. I'm not interested in the value. I'm interested in the process. What do you do? Okay? Because as soon as you throw an unknown in there, it's about what do you do with this? What are the larger properties of the numbers? And it's not about the specific results themselves. It's just like here. I should be able to say what x plus x plus x plus x is all the time without necessarily knowing what the value of x is. It's 4 times x. Granted, I don't have an exact answer at the end, but I have an expression that's equivalent to it. Okay? So when I look at this, I am looking for the sine of theta is going to be, this time, y over r. Basically the same thing. But now I don't know, okay? Well, I don't know what y is, but I don't know what r is. And so over here, I look at this, I've got the 3 and I've got the y. Well, what can I do? Well, you ask yourself, well, what did I do when I knew the value? Well, when I knew what y was, I used the Pythagorean theorem. So it's the same thing. It's just that this time, instead of putting a 4 there, I put a y, which in my case actually looks very similar to the 4. So 3 squared plus y squared is r squared. It doesn't stop me that I don't know what the value of y is. I just keep going. 3 squared is 9. Y squared is y squared. Okay? Now, at this point here, there's not a lot else I can do. Okay? I can't square the y. I don't know what it is. I can't add it to 9. They're unlike terms. So is that a dead end? Well, no. I am going to continue to write plus y squared because as soon as I know what the value of y is, that's what I want to do. I want to square it, then add it to 9. Well, assuming that I knew that value, what would I do? Well, I would take the square root to get r. So r is the square root of 9 plus y squared. As soon as I know what y is, I'm going to do this and get that answer. And then I will square root it. But I don't know what it is. All I know is that if I did know what it is, that's what I would do. I would go 9 plus y squared and square root it to get my r. Now, there's not much I can do about that because the way the properties of numbers works, the last thing I would do here would be the square root, and I would use the positive square root. Now over here, the sine of that angle, well, I don't know what y is, but I know that y would sit in the numerator, and I can now replace the denominator with the square root of 9 plus y squared. And that's what I'm asking for. Okay? As soon as I know what y is, I can plug it in, get an answer. Okay? But I don't know what it is at this point. So then the question becomes, well, what do you do with y if you know what it is? And this is what I do. And so my expression here, my final answer, is more of an indication of what I will do with that value once I know it. Okay, now what we're going to do is I'm going to show you an expression here. I'm just going to pull this one out here. Now we're going to come across to the other side of the sheet here, and I'm going to show you D. And what I'm going to do here is I'm going to give you this function here, y is equal to, and let's say it's 4x cubed plus 5x squared. Why not? And let's say that this is all to the 10th. Now, and I'm going to ask you now to take the derivative. Now we're going to slide ahead quite a ways. So now we're into calculus here. Well, you've done this rule before. You recognize that this is the chain rule. So your derivative would look like this. It'll be the derivative of that outside function, so 10 multiplied by 4x cubed, whoops, plus 5x squared to the 9. And now I'm going to multiply by the derivative of that inner function, that 4x cubed plus 5x squared. So that will be 12x squared plus 10x. Okay, and then there's your derivative. Now, granted, I would probably end up doing a little bit of simplification. You're probably multiplying the 10 through, or even factoring out, what do we got here, like a 2x here. For right now, that's not my goal, and in fact, if I did that at this moment, that might actually confuse what it is that I'm trying to really accomplish here. But this is your chain rule. So this is the outside. Okay, it's just the outside. The inside stays the same. Then I move in and take the derivative of the inside. Okay. Now what I want to do is very similar to what I have just done in the last two examples here. Okay. Now what I'm going to do is I'm going to say that y is equal to, let's say, u to the 10. Now the assumption here is that u is some function of x. I don't know what it is. I don't know what it is. But I know that it's a function of x. Just like up here, I knew that x referred to a number. Okay, just like over here, I knew that y refers to a number. I don't know what the number is. What do I do with it? Here, I don't know what u is, but I know it's a function of x. So now just take a look at what I did here. When you took the derivative, okay, the first thing I did was take the derivative of what was outside. Okay, well, what's outside of u? Well, it's u to the 10. So I'm going to take the derivative of u to the 10. That's going to be 10 u to the 9. Now, up here, when I did know what u was, I then multiplied by the derivative of what was inside. Well, u is what's on the inside. If you really want to see it, I would put parentheses here to try to make that as abundantly clear as possible. U is this function on the inside. To the 10th is that function on the outside. So bring down the 10 u to the 9, and now I'm going to multiply by the derivative of what's inside. That's exactly what I did here. But the thing is, I don't know what that is. I don't know what the derivative of u is. That's fine. What you do is you multiply by some sort of symbol that indicates the derivative. Like, let's say u prime. Okay, or you might even do it like this, and in fact you will see me do this a little bit later here, where we'll write 10 u to the 9, and then we might write du by dx. Actually, I would probably write this as dy by dx before I use that notation over there. Okay, this is the essence of implicit differentiation. Okay, when we know that there's a symbol in here that represents a function of x. So when you take the derivative, like right here, this is a function of x, but it's a nested function. I've got this outer function, I've got this inner function, I bring down the 10, inner function to the 9, multiplied by the derivative of the inner function. The question then becomes, well, what happens when you have a symbol that represents a function? It's the inner function here, but I don't know what it is. Well, all I know is that when I take the derivative, I would take the derivative of the outside, and then I would multiply by the derivative of that inner function there. That's that u primed right there, and that you need to always include that. Implicit differentiation is what we do when we have a variable that represents a function that we don't know. And it's giving me this indication of what I would do when I knew what that function was. I would multiply by its derivative. Just like over here. As soon as I know what y is, I'm going to square it, add it to 9, square root it to get my denominator. Here, Once I know what u is, I'm going to plug the u inside here, and then I'm going to take the derivative and multiply out by the back end. Okay? So that is the essence of implicit differentiation. Now what we're going to do is I'm going to lead you through a little bit of a note here, a bit of a discussion about the derivatives that we've been doing thus far and how it relates to this idea. Okay, and hopefully kind of at the end here, you'll see how all of this really comes together, and we'll do some examples to show you how this works. Okay, so now coming back to my notes here on implicit differentiation, just notice that like prior to this lesson here, all of the functions that we've been working with, okay, have been written explicitly in terms of x. Okay, so you have been doing explicit differentiation up to this point because you knew exactly how y was a function of x. Okay, we could write it out. Okay, not only do we know that y is a function of x, but we can see exactly how it works. So you can see the dependence of y on x. Okay, it's made, like it says here, it's made explicit in the representation of the function. So for example, we would have something like y equals x squared plus 5x minus 3. Okay, when you take the derivative of that, okay, y primed is equal to 2x plus 5. There's no real issue there. It's not difficult to do because you know exactly how y relates to x, and it's easy to find the derivative based on that. Now, sorry, sometimes it's inconvenient, okay, and that is a consideration. I know, I mean, you might look at that and say, okay, come on, it's inconvenient, but you can still do it. But yeah, sometimes it's inconvenient to the point of being like really awkward, or sometimes it's even impossible to find the explicit relationship between x and y. Now, that is going to come across as a little new to a number of you because up to this point, that really hasn't been the case. I mean, almost all of the math that you've done has been y equals some function of x. Okay. In fact, it's very likely that it may be the only example that hasn't been that has been the equation of a circle, x squared plus y squared equals r squared, where you couldn't just isolate the y nicely. It had to break into two functions there. But even then, you probably didn't even consider that was a little weird that you were breaking that into two. That the easiest way to write the equation of the circle was to have it x squared plus y squared equals r squared, where you didn't split up the y. Okay, so anyway, in those cases here, what we do is we simply find the derivative of both sides of the equation. So the derivative becomes this operator in now a very real sense, where we perform this operation and we do it to both sides of the equation. And we're going to find the derivative with respect to x. X is still the independent variable. Okay, y is still the dependent variable. And then what we do is we solve for the y prime term, the derivative of the y that is going to result from taking the derivative of a term with the y in it. Now, we saw that just a little while ago, where I was showing you how sometimes you might know what's going on with a function, but you might not know what the function itself is. Like I might be squaring a function, or in the example I used a few minutes ago, I took a function to the 10th power. So the derivative became 10 times the function to the 9 multiplied by the derivative of the function. Well, maybe I don't know exactly how y depends on x. Maybe I don't know exactly what that function is. So what I do is I use this y primed to represent the moments where I would multiply by the derivative of that inner function, and that inner function being y here. Now, let's take a quick look at just a couple of examples here. So for example, let's find y primed where we're looking at the function xy is equal to y plus 5. Now, so method number one is to go back to our old way of handling a problem like this, and that is to make it explicit. Okay, it's not always possible, but in this particular case, it is. So it is possible to solve for y. So what we're going to do here is we're going to bring that y over to the other side. So we get xy minus y equals 5. Then I've got a common y to both of those terms, so I'll factor it out. And now I'm going to divide both sides by x minus 1. And then because I find it easier to use the chain rule than, let's say, the quotient rule here, I'm going to write this as 5 multiplied by x minus 1 to the negative 1. And now I'm just going to take the derivative as usual, bring down the negative 1 to get negative 5, x plus 1 to the negative 2, or negative 5 over x minus 1 squared if your teacher prefers that you write these things with positive exponents. Okay? So I could do it like that. Or, and bear in mind what the derivative is here. Bear that in mind. We're going to come back to that in just a moment here. Or you could take the derivative implicitly. Now, what I'm going to do here is I'm going to now take the derivative of both sides with respect to x. Now, that's what this d dx is. D dx is. D dx is. It's this differential operator, which is just a fancy way of saying is like this is the thing that's going to force us to take the derivative. It's like this is what's telling us to take the derivative. It's almost like putting like a sign operation. I'm taking the sine of this, or whatever, except sine wouldn't distribute like that. But anyway, the derivative does. So now what I'm seeing here is I'm taking the derivative of x multiplied by y. Now, y is some function of x. I don't know what it is. It's replacing some larger function. So what that means here is that there are actually two different functions. There's the x function and the y function here. So how do I take the derivative when I'm multiplying two functions together? Well, I use the product rule. So this is x multiplied by the derivative of y plus y multiplied by the derivative of x. Now take a look at this. This is where this becomes really clear. Dx by dx is really just going to become 1. Dy by dx, I don't know what that is. And so the symbol that I've been using to represent that is y primed. So on the left-hand side, that quickly becomes xy primed plus y times 1. Okay. Over on the right-hand side, let's go up here, the derivative of y with respect to x. Okay, well, that's just y primed. Again, that's the symbol that I use to represent that derivative. I don't know what the derivative is supposed to be because I don't know what y is. At least I'm assuming in this case that I don't. I mean, we already saw that a moment ago, but let's assume that we don't here. And then over here, the derivative of 5, well, that's just 0. Okay, so now I've got xy primed plus y is equal to y primed. Now, the differential operator, okay, again, this thing that tells us to take the derivative is what we call linear, okay? And what I mean by that is I should be able to now solve for y primed. So I'm going to bring this y primed over. That's why you're seeing xy primed minus y primed, and I'm going to bring this y over. I can factor the y primed out. Okay, and so I get this y primed x minus 1 equals negative y, and then I divide by x minus 1. But bear in mind, y is equal to, and we did this before. Now, you won't always be able to do what we're about to do here. Okay, I want you to understand that this step right here, going from here to here, is only here because I know what y is, or at least I could figure it out. And I'm trying to show you that the results are the same. But I know that y is going to equal 5 over x minus 1. And so when I put that back in, I get negative 5 over x minus 1 squared, which is exactly the same as what I had before. Okay, so that's what this little bit right down here is about here. So notice that we need to solve for y primed, but that you do get the same result as before. Now, just so that you're aware, you will not always be able to get your derivative, okay, as a function of just x. Okay, sometimes you're going to have to leave the y in there. Okay, so let's take a look at this example right here. Find the derivative of 3x squared y minus x squared y equals 6. Okay, now first of all, I want you to notice, okay, that this is a function of both x and y, but notice that we've got a linear value of y here and a quadratic value of y. Now, could I solve for y? Yeah, but I'm going to end up finding that because y is quadratic here, that I would have to use the quadratic formula. It's going to break that up into two different functions here. Okay, or I'd have to try to factor that. It's going to get messy. So this is going to be very, very difficult to do. So the easier thing to do here is to simply take the derivative of all of the terms here. So I'm going to apply this differential operator. So d by dx, okay? So now that's going to be the derivative of 3x squared y. Okay, and remember this differential operator gets applied to everything. So this will be d by dx of xy squared as well, equals on the right-hand side, because you got to do it to everything, d by dx of 6. Okay, now this first term here, this 3x squared y, remember that y also refers to a function of x. I don't know what it is, but it is a function of x. So what I've got here are two functions of x multiplied by each other. So what I got to do is I got to split this up. So the very first thing I'm going to do here is take the derivative of 3x squared. That is going to be 6x. And then what I do is I multiply that by y, the second function. And then the product rule tells me that I'm now going to add. Now I'm going to add the derivative of y. Okay, the derivative of y. Well, what does y represent? What function does y represent? I don't know. I don't know. But I do need to take the derivative of y. So the best thing that I can do here is to simply include a symbol here that represents the derivative of y, or y primed. And then I'm going to multiply that by the other function, that 3x squared. Now, I'm going to subtract from that, because of the subtraction in between, the derivative of this other term here. Now, again, I'm seeing an x and a y squared there, so there's two different functions. I'm going to put this in parentheses, okay, because that negative in front, okay, this negative right here will distribute through after I'm done doing this. So I'm going to take the derivative first here, and then I'll distribute through here. So now I'm going to take the derivative of the x, because remember, there's two different functions here. There's the x, and then there's this y squared. Okay, well, the derivative of x is just 1 multiplied by the second function, y squared, plus, now, the derivative of y squared. Okay, now I'm doing something to this function. I know that y is a function of x, but now I've got this other function there. I'm squaring it, so this is going to be 2y to the 1, and then I would have to multiply by the derivative of what's inside. I don't know what that is, so I'm just going to write this symbol y primed to indicate that there is a derivative there. And then I would have the x left over, okay, from the product rule. That's the multiplied by the other function. And this is all going to equal the derivative of 6, which is just 0. Okay, that was my derivative step. Now what I got to do is get y primed by itself. So that is really just a little bit of algebra. So here's my 3y primed x squared, and I just brought the 3 up front because it looks better, minus y squared minus 2 y primed. I'll put the y primed at the end there because, again, it looks a little bit better. Okay, well, now let's leave the y primed terms together on the left-hand side here. xy primed. And I'm going to take my other terms over. So now that'll be that negative y squared will become positive y squared, and that 6xy will become negative 6xy. Here I will factor out my y prime term, and that should always be fairly easy to do. Okay, when we take the derivative implicitly, that shouldn't generate a situation where it's hard to solve for y prime. It should actually be pretty easy. So now over here, this becomes y squared minus 6xy. And now I'll simply divide to get y primed by itself. So y squared minus 6xy over, just wait for the computer to catch up, and that'll be 3x squared minus 2xy. Good. Now, that might be good enough, or your teacher might want you to factor out a little bit. Now, there's not really much I can do. I can take out a common y out of the numerator to get y minus 6x, and I can take an x out of the denominator to get 3x minus 2y. But that's about it. That really, there's nothing that cancels as a result. So I would argue that either one of these particular solutions is correct there. But there we go. That's how we use implicit differentiation to take the derivative of a function here, where it's not easy to solve for y or the dependent variable. Okay, and notice that this is in. Okay, notice y primed, okay, is in terms, and it's going to come up here in just a second, is in terms, oops, oh, that S looks terrible, of both X and Y, okay? And that will often be the case when you're having to take the derivative implicitly. All right, let's have a look at another example here. Find the slope of the tangent to root y equals root xy minus 2 root x, where x is equal to 4. Now, this is going to be a really good example to give you an idea of the overall flow of the way a lot of these questions are going to work, because there's a little bit more involved here, okay? But to start off with, we know that if we're looking for the slope of the tangent, we need y primed. We need the derivative, okay? And so what we're going to do here is we're going to rewrite this. I'm going to rewrite this so that I'm not working with radical notation anymore, so that I'm dealing with exponential notation. So this will be, or exponential, I mean just exponents here. So y to the 1/2 is going to equal, now because this is x multiplied by y, I can get x to the 1/2 here, y to the 1/2 minus 2x to the 1/2. Okay, and again, this is in terms of y. Now, I very likely could get y by itself here, okay, just by bringing some terms over and dividing here. But that's not the point. I want to, again, illustrate how you could do this implicitly. So I'm going to take the derivative dy by dx, sorry, d by dx of y to the 1/2 is going to equal d by dx of x to the 1/2 y to the 1/2. Okay, now I'm hoping I wrote that. Okay, minus d by dx 2x to the 1/2. Okay, so that, remember, all that dy by dx is doing is saying take the derivative, take the derivative, take the derivative. Now, on the left-hand side, I've got y to the 1/2. And again, I'm going to keep saying this. I don't know specifically what function y is referring to, but I know that it is a function, that it's some relationship on x there. So when I take the derivative of y to the 1/2, that is going to be 1/2 y to the negative 1/2, okay? Because that's how you take the derivative of that exterior function. But then I'm going to have to multiply by the derivative of what's inside, and that's going to be y primed. Okay, no, not y to the 1, y primed. Okay. Over here, remember, this is two functions of x here multiplied together. So I'm going to have to do the product rule. So that'll be the derivative of x first, which will be 1/2 x to the negative 1/2. Okay, multiplied by y to the 1/2. That's not a problem. To which I'm going to add, this time it's going to be x to the 1/2. Now I'm going to multiply by the derivative of y to the 1/2. Now it's going to look exactly the way it did on the left-hand side. So it'll be a factor of 1/2 y to the negative 1/2. And then because I know that y represents a function, the chain rule would say that I would multiply by the derivative. And so there I go. So there's my y primed. And then this last term is simply going to be the derivative of 2x to the 1/2. Well, when I bring the 1/2 down, multiply by 2, 2 is going to cancel. And I'm going to be left with x to the negative 1/2. Okay, so now what I want to do here is I'm going to try to isolate the y prime. Okay, so I see two terms with y prime. One of them is already on the left-hand side. So I'm going to bring everything over here. And actually, I'll tell you what, even before I do that here, let's multiply everything through here by 2, just to get rid of the denominators before I move anything over even. So this is going to be y to the negative 1/2. Whoops. Y primed is going to equal x to the negative 1/2, y to the 1/2, plus x to the 1/2 y to the negative 1/2 y primed minus 2x to the negative 1/2. Okay, good. At least that way I've got rid of that denominator of 2. So now I'm going to bring over the y prime term. So this will be y to the negative 1/2 y primed minus x to the 1/2 y to the negative 1/2 y primed. Okay, just waiting for the computer to catch up here. Is going to equal x to the negative 1/2 y to the 1/2. Waiting for it. Minus 2x to the negative 1/2. All right, good. Now factor out the y to the 1/2. Sorry, not the y to 1/2, the y prime. That's what I'm looking for. I don't know why I would have said that differently. Y to the negative 1/2. Okay, minus x to the 1/2 y to the negative 1/2 will equal x to the negative 1/2 y to the 1/2 minus 2x to the negative 1/2. All right, and so we're almost at the end here, so I'm going to come up here. So now when I isolate that, I'm going to get y primed is equal to x to the negative 1/2. Now, and I see the x to the negative 1/2 is common to both those terms, so I'm actually going to factor that out, and that's going to leave me with y to the 1/2 minus 2 in the numerator, and my denominator, okay, is going to be, and notice there's a y to the negative 1/2 common to both of those, so I'll take that out, y to the negative 1/2, and that is going to leave me with 1 minus x to the positive 1/2. Okay, now I'm almost there. These two terms here both have negative exponents, so they're going to jump to either side here. And now what I'm going to do, either side of the rational symbol there, the division. And now I'm going to put the radicals back in because it's going to look a little bit better with the radicals. And this will end up being root y multiplied by root y minus 2 over root x multiplied by 1 minus root x. Okay, good. That should come up here in just a second. There we go. Now, that's my derivative. I hope that made sense. Okay, I hope that made sense. Now what we're going to do is we got to evaluate that where x is equal to 4. Now, when I do that, if I evaluate where y prime, where x is equal to 4, now I'm going to get in my numerator here, that is still going to be root y minus 2. Now I could multiply that out, but I could also leave it like that. My denominator is going to be, well, take a look at what's inside here. The square root of 4 is going to be 2. So inside the parentheses, I'm going to have 1 minus 2, or negative 1, multiplied by the 2 out front there. So it's going to end up being negative 2 down there. Now, I need to figure out what y is, okay, before I can figure out what y primed is. So what I got to do is I actually got to go back to my original. So I got to make myself a little bit of room here. Actually, wondering where I can do this. Let me see if I can slide this down a little bit. Actually, so what I'll do here is I'll do just a little aside here. Do my work down here. So for the moment here, and this isn't great organization, I apologize for that, but anyway, I need to get what y is when x is equal to 4. So down here, root y is going to equal the square root of 4y minus 2 root 4. So this is going back up to the original equation so that I can figure out what y is so I can plug it into my derivative. Now, that's going to be root y is going to equal, well, the square root of 4 is going to be 2 root y. And this expression here, the square root of 4, that's 2. So 2 times 2, there's 4. Now, by just rearranging this, I will get that 4 is equal to root y, and square both sides, and I get that y is equal to 16. Oh, which is a nice number here, which is a beautiful number. So now I can come back up to my derivative here, plug that in, and root 16 is simply going to be 4 multiplied by 4 minus 2 over negative 2. Oh, waiting for that to come in. Whoops. Okay. Why won't that come in there? Okay, so 4 minus 2 is 2. The 2's will cancel, but I'm still left with a negative. And so my answer is negative 4. So the slope of the tangent to that function
is negative 4.